So one of the early solutions that were discussed, and this is a software based, so we're not yet at the hardware based. So one of these early solutions is called the Peterson solution. It only works for 2 processes, cannot work for more, and it is based on the assumption that these basic instructions, the load and store, are atomic. And atomic means that the instruction cannot be interrupted while executing. So when a load operation is currently on the CPU, it cannot be interrupted by any other instruction, okay? And so this Peterson solution is using 2 shared variables between these 2 processes. One variable is called turn. It simply represents, so let's say I have 2 processes, I and J. So if turn equals to I, this means that it is the process's I turn to execute in the critical section. If turn equals J, then it is J's turn. And then we have a second shared variable, which is called flag, and it simply represents the readiness of the process. So if flag I is true, this means that process I is ready to enter the critical section. This is what the Peterson solution looks like, right? Let's say this is the process PJ, okay? So we'll start by making sure that the process announces its readiness. So we set flag J to true, and then the process sets turn to I. So here, the process PJ is giving the other process, which is PI, a chance to run, okay? And then we have this, so it's setting turn to the other process, which is I. And then we have this while loop right here. So while flag I and turn equals I. So this means while the process PI is ready, and while its process's PI's turn, you can notice that we have the semicolon here. This means that this is an empty loop, which we call a busy loop or busy waiting, okay? So this means that process PJ is saying as long as it's process PI's turn and process PI is ready, then I will just wait here. I will keep spinning in this while loop until one of these 2 conditions are broken or they become false, okay? And once this happens, so either this one becomes false or this one, then the process is allowed to enter the critical section, okay? Otherwise, it will keep spinning here. It's not allowed to enter until the other process allows it to, okay? And then at the end, we have the process PJ setting its own flag to false, so it's announcing that I'm not now ready, I'm done, I'm exiting the critical section. So this is the exit in a section, and this is the entry section. This is, of course, our critical section, and this is the remainder section. If we put both the codes next to each other, this is what it will look like, right? So this is the code for process PI, and it's the same thing for process PJ, except the indices are different, right? So here we're talking about flag I because it's process PI, and then we're talking about flag J because it's process PJ, okay? So in order for us to prove that one solution is actually solving the critical section problem, that solution has to satisfy these 3 main requirements, okay, or conditions. The first one is mutual exclusion. So the solution has to make sure that, as we said, only one process can enter the critical section at a time. So no other process can be in the critical section if one is currently executing, okay? That's called mutual exclusion, okay? The second one is progress. So the solution that we propose should make sure that no process gets put on hold forever or indefinitely. All processes should have a chance of entering the critical section should they want to, okay? And then the bounded wait simply means that once a process announces its readiness, it should only wait for a finite number of turns before it gets to enter the critical section, okay? So when you want to prove that one solution is a critical section solution, you always have to prove these three conditions are satisfied, okay? So if we want to prove that the Peterson solution is actually a critical section solution, we could start by the first one, which is mutual exclusion, okay? So we know that there is no way that both processes can be both in the critical section at the same time, right? Because let's say this is process PI. So we said that process PI will be stuck in here, spinning in this while loop as long as process J is in the critical section. It can only enter the critical section if one of these becomes false, right? So either the turn will now be I, okay, or the flag J becomes false, okay? And flag J becomes false only when process J exits the critical section, okay? That's the only time we allow process PI to proceed. We do have progress because, as we said, once one process is finished, it sets its own flag to false, and that's simply to allow the other waiting process to execute. So we can't have one process that's blocked indefinitely. Both of them get a chance to run when the other one is finished. So, and then lastly, if we talk about the bounded wait, we know that it is bounded to one turn. So right after J executes, it cannot run again. Okay, so when it sets its own flag to J, it is now I's turn to execute. We know that the bounded wait is one iteration. So this example right here is another example that's asking here whether or not this is a critical section solution. So in class, I give my students some time to do this one, but in the lecture, I will just go quickly over it. So you can see that we have two processes here, A and B, right? We do have some attempt to synchronize, right? So we're trying to set the flag to true, we're trying to set turns right here, but right after that we have the critical section. So there is no busy wait here. There is no while loop that will stop the processes from entering the critical section, okay? This means that the first condition is violated, which is mutual exclusion. So this is not a critical section solution. Now, the problem with the Peterson solution is, first of all, it works for just two processes, and second of all, it under these modern architectures where we have multiple CPUs, this solution does not work correctly, okay? And if we have multi-threaded applications and we have multiple CPUs, sometimes the processors, they tend to change the order of instructions to gain some performance advantages, but that will make this Peterson solution not valid as a critical section solution. So to give an example of how the reordering of instruction may happen, we have these two threads right here. So thread one, currently, so we have these two shared variables. The flag is set to false and x is set to 0, and then we have these two threads, okay? So thread 2's job is to set x to 100 and flag to true, while thread 1's job is to test for the flag. So as long as a flag is false, it's waiting, right? So it's doing nothing, it's just spinning here. And when the flag is set to true, then thread 1 is supposed to print the value of x. So from these two threads, we could expect that this process is trying to print, so the expected output should be 100, right? So once thread 2 sets flag, it sets x to 100 first, and then it sets the flag to true, which will allow thread 1 to break from this while loop and print 100, right? Now, what happens if we have multiple processors and thread 2's instructions are reordered? Okay, so if we go back, this is thread 2. What happens if these two gets reordered? So flag first, true first, and then X is 100. So what will happen here is thread 1 will actually output 0 instead of 100, okay? Now imagine that the reordering of instructions happened, and this is the Peterson solution. So let's imagine that these two lines of code got reordered. So we start with setting turn first and then flag. So and then let's imagine that we have two processes, P0 and P1, right? And this is time, right? So initially P0 starts executing, it sets turn to 1. Right after that, P1 executes and it sets turn to 0 and flag 1 to true, right? And then, so since the turn is equal to 0 and flag 1 is equal to true, but flag 0 hasn't been set to true yet, it's still false. So this means that process P1 is ready to enter the critical section, but process P0 is not. So this means that process P1 can now proceed and enter the critical section. And then right after that, we have process P1 now is allowed to run on the CPU, and it executes and finishes the second line of code, which is setting flag 0 to true, right? So now P0 detects that flag 0 is true, and turn, we're going to check the last value of turn is 0, right? So since turn is 0 and flag 0 is true, this means that its processes P0's turn and it is ready. So it will also enter the critical section. So you can see that at this point, both processes are in the critical section at the same time, which violates the mutual exclusion condition, right? So this means that this very simple solution not only works for two processes, but also is not effective in modern architectures.